Okay? Sure? So, now think of a chi-square distribution with m degrees of freedom. Okay? Think of dividing this by its own degrees of freedom. Statisticians do these kinds of things. Right? Think of a chi-square distribution with n degrees of freedom and think of dividing it by its own degrees of freedom. And then finally think of dividing the first by the second. What you get is called an F distribution with n and m degrees of freedom. So what is the F distribution? It's the ratio of two independent chi-square distributions divided by their own degrees of freedom. Right? The F distribution is the ratio of two independent chi-squares divided by their own respective degrees of freedom. Yeah, the F distribution is nothing but the ratio of two independent chi-square distributions divided by their own degrees, their respective degrees of freedom. Here, n is mn. M is called the numerator degrees of freedom, n is called the denominator degrees of freedom. M is called the numerator degrees of freedom, n is called the denominator degrees of freedom. Now what is the point of doing all this, dividing a chi-square by m and all that, right? Okay, the point is as follows. See how we can use it. How we can use it. Suppose you got two samples. Okay? Suppose you have x1, x2, xm coming from a normal distribution with say mu1 and variance equal to sigma square 1. Okay? Suppose you have y1, y2, yn are all independent and identically distributed samples coming from a normal distribution with say some mean mu2 and variance sigma 2 square. Alright? Suppose you want to test h naught, that sigma 1 square is equal to sigma 2 square against the alternative, that is we are testing whether the variances of the two populations from which these samples have come is identical. Right? Variance of the populations from which these samples have come is identical. Right? That's what we want to study. Now from the theorem that we have just studied, so how does one tackle this problem? In the chi-square distribution we learned to test hypothesis about an individual population variance. Here we are comparing two samples and seeing whether their population variances are the same. Right? So what do we do with this in such a case? In such a case, remember, can I work this off? Okay. From the first, or let me not. From the first, I know that if I write S1 square as summation xi minus x square upon m minus 1, that is a sample variance from the first sample. Right? Let S2 square be summation yi minus y bar square upon n minus 1. Right? So we know now, we know from what we have just studied that S1 square upon sigma 1 square into m minus 1 is a chi-square m minus 1 from the theorem that we have just done. So if I divide this by m minus 1, this is a chi-square divided by its own degrees of freedom. Right? Sure, similarly I know that S2 square into n minus 1 is a chi-square with n minus 1 degrees of freedom. So if I divide this by n minus 1, this becomes a chi-square divided by its own degrees of freedom, right? So if I divide these two, right, if I divide these two, I should get a ratio of two independent chi-squares divided by their own degrees of freedom. Yeah? So this ratio must be an f with m minus 1, n minus 1 degrees of freedom. Right? But this is really useless to me at this point because I can't calculate this ratio. The reason is I don't know what is sigma 1 square and sigma 2 square. This can go, this will go, this will go, right? So what is really left is s1 square upon sigma 1 square whole divided by s2 square upon sigma 2 square. From the null hypothesis, however, what do we know? The null hypothesis sigma 1 square is equal to sigma 2 square. The null hypothesis is sigma 1 square is equal to sigma 2 square. Now if the null hypothesis is indeed valid, then you can cancel these out because this and this are equal. So what you then get is s1 square upon s2 square must be an f distribution with m minus 1 numerator and n minus 1 denominator degrees of freedom. So in effect, to compare two independent sample variances, right, and to confirm whether they come from the same population variance or not, you have to take the sample variance from the first sample divided by the sample variance of the second sample. The ratio will be an f distribution with m minus 1, where m is the number of observations in the first sample, and n minus 1, where n is the number of observations in the second sample, n minus 1 degrees of freedom. You will have the f distribution, and then you must compare the the lower 2.5%, upper 2.5% if you are using a 5% level of significance, and then see whether this calculated statistic lies in the rejection region or not, and that will help you reject the null hypothesis, right? That will help you reject the null hypothesis. The final distribution, so that's the f distribution. Is this clear? Right? Okay. Finally, a very useful distribution that we are going to have is what is called the student's t distribution, which is also derived from the chi-square distribution and the standard normals really. Okay? Right? So, think of a standard normal distribution. Okay? Think of a chi-square distribution with n degrees of freedom. Okay? Think of dividing this by n. Think of taking a square root of this. And think of dividing z by this whole contraption. Right? Then the resultant is called a t distribution with n degrees of freedom. The distribution followed by this quantity is referred to as the student's t distribution with n degrees of freedom. Why should you remember this rather convoluted formula? Because think of a standard normal, right? Think of, say, x bar minus mu by sigma by root n is a standard normal. But if you do not know sigma, you cannot take test of hypothesis, right? You also know that s square upon sigma square into n minus 1 is a chi-square with n minus 1 degrees of freedom. So if you divide this by n minus 1, you have a chi-square. You have a chi-square divided by its own degrees of freedom, right, as you have here, right? So this will go, take the square root and divide. You must have the student's t distribution, right? But this is what? This is x bar minus mu by sigma by root n divided by s and sigma, which is what? S by root n. Right? Now what we have been able to do is replace the unknown population variance by the known sample variance, S. with the result that this is now a t distribution. This now follows the student's t distribution with n minus 1 degrees of freedom. So the difference between the student's distribution and standard normal is the z distribution is the population variance is given in the z distribution. If you replace the population variance, the known population variance in the z distribution with an estimate of the sample variance, S square, S, from the sample, the resultant is no longer a standard normal, but a t distribution with n minus 1 degrees of freedom. Yeah, with n minus 1 degrees of freedom. Is this clear?